recording. Now we are recording. Welcome to the evening of Python coding. In this meetup, it usually started in Austin. For many years, we had a demo each month or so. We have a demo about some Python library. So this expanded to DC a few years ago. Now I find myself in Israel, and now it's war in Israel. So you probably heard about the atrocities that happened here, and Israel went to war. I'm still keeping this meetup though for all the people in the US. So please, we're still doing Python even under fire here. So, and today, actually, the speaker today had to bail out because of the situation here in Israel. He was also from Israel, but Kevin Kho, who already gave us several demos in the past, very interesting ones. He jumped in and said, "Oh, I have a demo for you." So he's going to talk about hierarchical forecast. And Kevin, the floor is yours. Show us what hierarchical forecast is.
Yeah, thank you. So before I share my screen, just a couple questions for the people in the room, just so I know who I'm talking to. I guess number one, because I know like Python can also mean like web dev or anything like that. So I just want like checking, uh, is there anyone here who like doesn't work with data, for example? And then I guess are there also people who are relatively new to Python? So I know what like if there's anything I should explain more. So it would help me if you just like put a quick um, a quick bit of your info in the chat. Um, and then uh, I also this demo that I have today will touch also on data at scale. So I don't expect a lot of people in this room, but I also want to ask: is there anyone who has experience with like distributed computing frameworks like Spark, Dask, and Ray? Oh, and then also last guiding question, I guess we're doing time series forecasting. So does anyone already have experience in time series forecasting? Um, okay, so someone wanted to raise their hand. I think was it you, Lolan? I don't know how to pronounce your name.
Oh yeah, just saying that I have experience in time series and distributed processing.
Okay. Oh, both? You
Yeah,
have
yeah,
experience in both?
a little bit. Yeah. Not a ton, but uh, worked with Dask and also there's not like a particular library for it, but when you manually distribute processing across cores and things like that and across servers.
Okay.
Sure.
Okay.
I
Okay.
probably just put it in the chat rather than say it out loud here.
No, no, that's fine. Anyone else want to voice it in the chat? You're welcome to. Uh, no one else. Is there anyone who's coming from the web dev side? Um, Kev, I see Kevin said he knows Raft. What is Raft, Kevin? I'm not familiar with Raft. And then I
It
guess we have, yeah, go ahead.
it's like a project. Well, when I was in college, it's a distributed system course, and WAF is one of the projects where you
Ah,
distribute the nodes or the system between different processing operations and make everything up to date and stuff and such. Yeah.
gotcha. Um, yeah. Okay.
The
Um,
leaders and co-leaders was the newest
yeah.
update of between different system across different part of the operating. You know.
Okay. Okay. No, that's like too low level than what we're gonna do today. So this I see we have a lot of people new to Python, and I want to mention like if there's literally any question, just feel free to interrupt me. No, all questions are welcome. We also I guess have some data people. Okay, someone knows Modin. And we have a couple people who are just new. That's good. That's welcome. So okay, a bit of so just to introduce myself. Um, I uh, so my name is Kevin, currently based out of Chicago. I've been in the data space for 7 years now or something, between like across like many roles like data scientist, data engineer, machine learning engineer. I spent the last like 2 to 3 years or 2.5 years working on open source stuff primarily. So um, my last full-time job was with a company called Prefect, which is open source. And what Prefect does is, let's say you have a couple of Python scripts that you want to run in some certain order, and there's some interdependencies to it. Then, like for example, you want A to run, and when A finishes, you want B to run. And then depending on the output of B, you want to either run C or D. So this type of setup, this type of framework is called workflow orchestration. So I work for a and we see them used to schedule and monitor data pipelines. So I was with Prefect um, a year ago, and then I since left Prefect, and I've been working contracting on a bunch of open source stuff, mainly related to data at scale. So I have my own open source project, which we'll also cover today, that deals with simplifying data processing at scale. Um, Aside from that, I guess today's topic will be hierarchical forecasting. So hierarchical forecasting is when you have um, sort of these. So you have forecasts that you want to add up, and you want the forecast at each level to be equal to each other when you sum them up, right? So for example, you want to do like I know someone who works for Chick-fil-A, and one of the things he does is, do you guys have Chick-fil-A in Texas? I have no idea. But anyway, I hope you guys all know what Chick-fil-A is. What he does is they actually forecast um, the amount of ingredients at every store, right? Okay, you do. So for example, how many tomatoes does the store need? How many like burgers, chickens does the store need? And but then, maybe the fleet that delivers those ingredients uh, doesn't just deliver to one store, right? So they have to deliver to multiple stores at once. So in addition to forecasting at the store level, you also need to forecast at like a regional level, and then maybe at the state level, right? So uh, if you simply use any time series forecasting algorithm, and you just say, let's forecast, this store and this other store and this other store, and then you also apply that same model at the regional level, what you'll often find is that the forecast, if you add the stores, does not equal to the forecast of the region, right? And so what hierarchical forecasting does is it reconciles all of these and make sure that they're all equal. So we'll be talking about hierarchical forecasting today. This presentation, I gave it in PyData New York last year. And, to be honest, I felt like a lot of people were just staring at me and not asking, like I lost them. So if there's any point where you want me to elaborate on something, like just feel free to ask more questions. Everything is welcome. So I'm gonna share my screen and show you what we're working on today. So I have.
Kevin, before you continue, this is part of the projects that you're in the company you're contracting with now, or
One of. So I contract for Nixla, which does a lot of time series forecasting. So this is one of the places I contract for right now. Yes. But this is open source. Everything that I will demo today is free, and you can just download it. Um, so I have this repo here, and I will paste it in the chat. And if you want to reference the code or the notebooks here after this presentation, like you can just come back. If you want to follow along, there's also a requirements.txt file so you can easily just pip install the requirements, and this should be you should be able to follow along with this. The notebooks are also well annotated. I won't. I may skip over some sections today, or I may add more detail. But in general, if you just want to read these notebooks, you can also do that. I also spent a bunch of time annotating them so that you could just read them independently. So this repo's in the chat. Feel free to clone and get and follow along. No need to really for today. We can just have a casual chat. And with that, I will get started. There's a couple of projects we will cover today. So the first one, of course, is hierarchical forecast, and this one is the one where you're forecasting many things, and you want them to get to be equal at all hierarchies, right? So this is hierarchical forecast. Uh, this so Nick's law, which so before you do hierarchical forecasts, you have to start with a base forecast. So what you do is you actually make those models at the store level, and then hierarchical forecast is more about reconciling those and making them equal. But before hierarchical, you also have to have these base models which you build on top of. So for that, we're gonna use stats forecast, also by Nixla, also open source. You can just pip install this. And then I will also, for scalability, I'm gonna show another project. This one is my own project. So I work on the Fugue project mainly, and it's meant to simplify using computation at scale, right? So if you have a cluster, we can bring it to the cluster for you, or we can use local multiprocessing. So we're going to use these three. And stats forecast, for those who are familiar with time series modeling, this is your standard like ARIMA, ETS, error trend seasonality, like these types of like statistical and econometric models. This is what stats forecast contains. So for those of you who may not be familiar with ARIMA or with time series modeling in general, there are a lot of time series models that they won't be the same as your like traditional like scikit-learn, linear regression, or anything like that. I mean they can be, but the point is that a lot of them really are specialized to handle time series, and like they look for they look for things like, oh, how correlated is the time series with its lag values and stuff like that. So time series has some specialized models. And with that, let's get started. So I'm just going to open these notebooks. In this repo that I shared, I have 5 notebooks, and I'm just going to go over, it's just 1 through 5. And we're just going to go through them today. So I have them open already inside my VS Code. I'll make this a bit bigger. Looking at the screen. Okay. And okay, so let's get started. So if you're not familiar with time series modeling, like historically, time series modeling in Python was kind of like a second-class citizen. A lot of the state-of-the-art implementations were primarily in R, and also speed-wise, Python was slower than R in a lot of these. So actually, my first, I see Alexandra here. You mentioned you're a GIS tech looking for a data analyst role. So when I started my data science career, before my first data science job, I was actually a hydrology researcher with the U.S. Geological Survey. So I actually dealt with a lot of times. We were forecasting rainfall, and in addition to rainfall, primarily we're for my first job. What we were doing was the in the Chicago region, we draw our water supply from Lake Michigan, and also the neighboring states. We all draw from Lake Michigan, and there are limits to what you can draw, but you can overdraw this month if it's if it will be replenished next month. So it only has to be balanced within a calendar year before you actually get penalized, right? So what we did was we forecasted rainfall, and we did a lot of rainfall simulations so that we could know, like, hey, in 75% of scenarios, the rain will be replenished. The rain will come in, and snow will melt and will replenish the level of Lake Michigan. So that was my first role. So that's where I started with time series modeling. And back when I was doing that in like 2016, 2017, I would say the Python ecosystem for time series modeling was very weak. So everything that we did was in R, like all the AutoArima packages. And so just some background on this company, Nixla. What Nixla does is they aim to uh, bring the state-of-the-art algorithms into the Python ecosystem. So this is, I would say, relatively new. Not really. I mean, maybe 2 years old. And they want to. So there were existing libraries like PMD Arima, stats models. They were orders of magnitude slower than than the equivalent R implementations. So what Nixla does is they there's this package in Python called Numba, over here, Numba. And what Numba does is it precompiles your code. So when you execute it, it can be a lot faster, right? So very useful for a lot when you're dealing with like stuff like NumPy matrices and like computation. So they use Numba heavily and re-implement the algorithms from scratch so that we can have a faster experience inside Python. So in general, I mean, I won't reread this, but in general, you're going to see that it is faster than R. Also, the AutoArima implementation is faster than R. And you can benchmark a million series under 5 minutes. I mean, this depends on your cluster size, but the point is that it's highly scalable, and you can forecast millions of time series. So something to point out for those who are less familiar is that when you do machine learning, like let's say we are predicting something like what, I don't know, struggling to think of a good example. But let's say it's a classification problem. You will collect all your data and you train one machine learning model on all of your data. In time series specifically, sometimes you may see that instead of one big model, we just have many smaller models, right? So with my example of Chick-fil-A, right, or a restaurant chain, instead of forecasting the whole, I mean, instead of making one model for all of our stores, what we may do instead is we may have one model for each store level, right? And then we have 1,000 stores, we have 1,000 models, and we treat them as independent things. So when I say you're gonna train 1 million series, this is like you have 1 million combinations of like product and geography, right? As we'll see in today's example. So you train what it becomes important then to use like multi-processing or to use distributed compute over a cluster so that you can um, you can train all these models in a reasonable amount of time. Because if you were to run this on a single laptop, like sequentially, this could take days or weeks, right? So you need to accelerate that. So now we're gonna reach some Python questions. Welcome. Just please interrupt me. So first, look at stats forecast. They have a utility function here called generate series. Leolin asked me what size of data do I work with. I will say beyond like 100 gig, the treatment is kind of the same for the most part. I mean, like as long as you can just use Spark or Dask. But so okay, so I should clarify here. It's not just the data size. So there's two scenarios where, hey, maybe I need to get more resources than my local laptop, right? One is data size, right? So like, hey, my laptop can only have 16 gigs of RAM. My data is 50 gigs. You need to do something. You need to get a cluster on the normally on the cloud, right? You need something, and that's what we call memory bound. And the second thing is, hey, like everything fits on my machine, but it's taking me 12 hours or 16 hours, right? Then at that point, the question is, okay, can I get more resources? And then can I uh, parallelize the execution of that and then collect the results? And that's what we call compute bound. So it may not just be the data size itself. It's also just like how long is it actually taking to do that computation. But me, myself, I've worked in the 100 gig plus range, but the same tools for like 50 to 100 gigs roughly will work also beyond 100 gigs. It just becomes a question of how much compute you have. Ahmed asked a question: how do you typically start a data science project? Do you come up with any code of your own, or finding a way to handle the data? Uh, okay, so number one, um, how I guess it varies depending on what kind of project you're doing, right? As we'll see here, time series requires its own format to process. Same thing if I mean the field because like ML is kind of broad. So if you're doing image or text, right, they have their own pre-processing as well. So it really depends. Do I come up with code of my own? I personally am working more on tools for data scientists these days rather than doing uh, machine learning myself. But I would encourage you to always like, of course, like if you happen to do time series forecasting, I hope you wouldn't rewrite your own time series forecasting library from scratch and you look for available things because the ecosystem is so big. Um, but I have also been in some situations professionally where that was not an option, and we had to create our own frameworks. Not I mean frameworks for like multi-processing and stuff, not necessarily the data science aspect. And then the last question you asked is it about finding ways to handle the data? Yes and no. Like I'm gonna show one way to do time series modeling today, but you may use other libraries also to just see if results get better. And then it would be a matter of, okay, like what format does the library that I'm gonna use require the data to be in? And then maybe you have to massage your data to fit that format. Um, so we have this utility function, generate series, and just for starters, uh, okay, David asked, can you speak about NHITs, neural hierarchical interpolation, uh, variational autoencoders, and transfer learning for time series? I can answer quickly that I cannot speak about that. I don't do a lot of deep learning myself, but Nixla has these NHITs and NHITs implementation available also, I believe, under the neural forecasting library. So that is there. And Nixla also has done a lot of work with transfer learning in time series. So I guess a bit out of scope for today, but I will just show it over here. Under the Nixla library, what you're looking for is neural forecast. And um, this is the one that contains NHITs, I think. And what for people who may not be like here, this is NHITs, what you're looking for. For people who are not familiar with this, what David's asking is like some people are starting to use neural networks in time series modeling. I would say it's a bit more experimental. And what transfer learning is in David's question is if we, like, for example, with image classification, if you have a million images and you train a model on all these million images, and then you have a model for that. And then that model, that big model, you want to apply to your use case. Maybe your specific use case is like, I make a car detector, right? Like what model of car is this? You can get that big model and you can just fine tune it a bit and it could apply for your use case. Or you could use that like, so what David's asking is like, if we train a model on several million time series, can we then just give it a random time series and get a forecast, right? So this is an open research question today that Nixla is specifically working on as well. Robert is asking, how do you measure success for your forecasting model? How do you approach interpretability of your forecast? How do you measure impact of forecast drivers post hoc methods? Ooh, unfortunately, I will not touch on that so much today, Robert. But I actually had this is actually kind of part of my presentation that I gave last week at the same meetup. So last week I presented on this thing called conformal prediction, and it was about like if you have a time series forecast. First of all, like success is just your standard metrics, right? Like how far it was from the actual, like things like that. Um, and interpretability, I think we don't have as much in time series with the statistical methods. But the more important thing with time series is like if I'm predicting X and like what is the error bound around it? Like what is the like 90% confidence interval around the forecast? More so than the actual, it's and actually I okay, in the topic of time series, I'll just talk about this. There was this library by Facebook, right? And they released a library called Prophet. Now, Prophet was a time series model designed specifically for Facebook applications. So, for example, something that Prophet had in their library was uh, holidays were like a first-class citizen of forecasting, right? And what they went on to say was with Prophet was that it actually was kind of designed for Facebook use cases, but maybe it did not generalize so well. So the author of Prophet, his name is Sean Taylor, is an advisor actually to Nixla today, and advocates that Nixla as one of the alternatives to using Prophet because he said that when he worked on Prophet, it was more like solving Facebook internal stuff and he didn't actually consult with the broader academic community around time series forecasting. Um, SHAP and line values, I don't. They so what Robert is asking about SHAP and line values is like, um, for example, if we look at, let's say we're forecasting housing prices, right, and we train a model using the square footage, using the number of uh, bedrooms, the number of bathrooms, and then maybe like, hey, is there a garden or whatever, like stuff like that. Now with Shop or Lime, what we can do is we can individually see how each of those impacted the forecast, right? So we can say if the bedroom moved from 2 to 3, what would the impact of the forecast be? Things like that. Um, and with time series, it's just not this. We don't have features in the same way, right? Because like some of these models just rely on lags and stuff like that. Lags, autocorrelation. So we don't have features in the same sense. So that's why I feel those set of model interpretability don't really hold as much in the time series domain. So what's more important from a business perspective is actually just getting your forecast, trying to improve the how your like historical performance, like how it would perform in history, and then what you do is you just get the 95% confidence interval and you plan around that. Um, yeah, feel free to message me, and I don't mind being sidetracked. Anything like it's just casual. Just feel free to interrupt me. Okay, so move unless there's anything. Moving on. Um, so here we're gonna generate two series. We have a utility function. We're just gonna generate two series, and then we'll see what these look like. So here is what just checking the size is fine. No, it's okay. So here, this is the data frame from our Nixla generate series, right? So we have a unique ID, and because we generated two, this will either be 0 or 1. And then we have a date, and then we have our value. And we have two forecasts, and I think we can just plot them using matplot as the seaborn line plot. And you're gonna see like this is the time series forecast with ID 0. This is the one with forecast with ID equals 1. So nothing. This is just a random series, nothing too fancy. And then we're gonna do some. We're actually gonna do the time series forecasting. Um, oh, and yeah, Rob. Someone. So Robert said he'll follow up online, and I want to invite everyone. Like, if you want to message me after the presentation as well, literally for anything, um, feel free to message me. I have people also messaging me for career advice. I try my best, but it's kind of hard right now as well. But I mean, I'm happy to chat anyway, uh, and brainstorm how you can improve your portfolio or resume. Always happy to chat. Uh, Leolin has a question for time series. The metric is MAE, right? And what he's asking is the MAE
Tell him,
is
tell him what MLE is.
yeah, MAE is mean absolute error, right? So it's like if my, let's say I forecasted 100 and the value was 110, right? Then my absolute error is 10. Same thing if it were like my um my forecast was 100 and the actual value was 90, then the delta is, I mean, it's negative 10, but absolute error would be 10, right? So Lowland's asking if the normal metric for time series is MAE. So one of the problems with MAE is like there's no concept of, for example, we're in a Chick-fil-A store and we have 100 chickens that come in a day. Something with MAE is like for example, store A has 100 chickens a day, store B has 200 chickens a day, and then the MAE for for store one, for store A is like, let's say we're off by 1 chicken, and for store B we're off by 2 chickens. The store B MAE will be higher than store A. So because like you're off by 2 chickens, but here you're off by one, right? So in a sense, the MAE is not always a complete picture of model performance because it doesn't take into account what the normal value is. And that's why there are other metrics you'll see, like for example, mean absolute percentage error, or like MAPE, where it's like your error will be 1/100, and for the other store it'll be 2/100. So you normalize it in some way. Um, so honestly, I can't say there's a best metric or anything, but you normally would just print out all the metrics and kind of gauge from there. Um, yeah. So now we're actually gonna hit the actual, like, we're gonna make some forecasts right now on this data that we generated, and this is just all the code that we need. Very simple. This will give us our time series models. So we import auto ARIMA and auto ETS. So ARIMA is a type of model, and auto ARIMA will like step through a bunch of ARIMA combinations and find the best ARIMA and then return that. And the same thing with ETS. ETS decomposes your time series into the error trend seasonality, and then it'll find the best fit model, and then return that. So I think by default it will use like RMSE or ME. I'm not sure. Um, so it will fit all that, and it will return. And this, so we pass in our series. We describe what models we want to. Yeah, we want what models we want to try. The We have to specify the frequency of our time series, and here we're saying daily. And then this n jobs equals 1 is the parallelization, right? So if you have 8 cores on your machine, it will use all the cores of your machine, uh, off the shelf, like nothing fancy for you to do, just it's all taken care of. Stats forecast will parallelize and use all available cores to your machine. And then you just say forecast, and you say when we say sf.forecast, so this is our stats forecast object. It has a forecast method, and when we say forecast 7, that's 7 days out. So we will get a prediction for 7 days out, and then we get sorry. So we get the auto ARIMA prediction and we get the auto ETS. And if you add additional models here also, then you'll just get them in another column as well. So that's it we need. That's the most basic thing. We got a forecast 7 days out, and then we can plot it. So here I do some don't be too worried about the transformations, but basically it's just a bunch of, we add in the predictions with our original time series, and then we predict we plot them, and you're gonna get something like this. So here is our, don't mind this too much. It's just because it's a demo, but for real data it'll look better. But here we have our ground truth, and then we plotted the auto ETS, and then we plotted the auto ARIMA. And this also, like, I think we have a question on metrics. I think there's also like visual can also help sometimes, I believe, in choosing a model. Here we have another one. There's a question here. Are we working in collab? No, this is just my local laptop, VS Code. But it is a Jupyter notebook in VS Code. Boy, says you're new to Python coding. I mean, feel free to ask any questions. I mean, this may be complicated, but I hope this should be pretty easily understandable. There's not much to it, and we were able to generate our time series forecast. So we have this time series forecast. We saw it how it works on some generated data. If you're more familiar with stuff like scikit-learn, the question is auto ETS stats forecast or SK time? The auto ETS I imported was stats forecast. There is another library called SK time, which is a time series library. Like they try to unify the API for time series, and I think into scikit-learn style, so like fit predict kind of method. I think so I will say one of the differences between stats forecast and SK time is SK time might even use like the stats forecast implementation. So SK time is more concerned about how do we have a unified interface for every time series library so that it's just fit predict, right? I think that's their concern and not necessarily about the implementation. Whereas stats forecast implements all of the libraries literally from scratch, right? So stats forecast is really like implemented, and that's why they can speed things up because of Numba. So we have this. If you're familiar with like scikit-learn libraries, you normally import your linear regression or your support vector machine or XGBoost or something, and then you call .fit, .predict. Time series modeling is a bit different from that, because normally if I create a machine learning model to identify like what kind of car this is, or like what kind of like food this is or something like that, I can create a model, and it's gonna relatively just be applicable in the long run, right? Any classification, or like even if housing prices, like I could maybe just rerun predictions, but relatively like that model will be fixed. But time series, as you can see here, if you look over here, you see this orange line. So with time series models, like you get more inaccurate the further out you are from your first prediction, right? So your error just accumulates. And because of that, the recommended best practice is that maybe you just create a new set of predictions every week and you try to run it every week. And that's our motivation for having a time series library that is fast in terms of execution. And also, that is also the motivation for just having this dot forecast over here. There's no fit predict. And So with scikit-learn and with other models, you normally fit something, you save that fitted object, and then when you're going to make predictions, you load it in the future, and then you apply that model and you say dot predict, right? So here we just do it. This is fit predict in one step, but the important piece is we don't save that intermediate object. But we also have that interface in stats forecast. You can just say model fit, model predict. This is the same thing. I'm just showing the full data frame now. We have 7 predictions for each unique ID. And what I'm going to show here is that inside this, so here we have this object called model, which is our stats forecast class. And this model has an object called fitted. And then you can check. So this is what the representation of our model looks like. And we keep the residuals for each. This is one model this was the best fitted model from the AutoArima. This is our residuals, and you can see that this can get big in size. So again, if we think of like one model for each like store, and we have 100,000 stores, then we can easily have 100,000 of these objects, and it can get very heavyweight. And that's why the recommended API is we just use this dot forecast straight up like this and get the predictions and serve them. Okay, now this is actually slightly outdated now. I won't go over this so much because we don't have a lot of distributed computing like folks anyway. But the point is that for this stats forecast can scale even to like 1,000,000 time series. Like there's no problem. Basically, what will happen is that instead of this over here, this is a pandas data frame, and if you wanted to pass a Spark data frame to it, the syntax would be something like this. From PySpark .sql and then we'd have a Spark data frame, and then this would just be SDF. So like this would be the syntax, and it would work off the shelf. So we literally don't have to change much. We're just changing the input data frame. And so if you're using like a cluster of machines, then you either have to use a distributed framework like Spark or Dask or Ray. And basically, whatever you use anyway, Spark, Dask, or Ray, it's all compatible with this stats forecast. You just have to insert it over here. And it would be the same thing for a Dask data frame. Dask data frame is meant to be like a distributed pandas. So you would import Dask.data frame as DD. And then you can say DDF, like my Dask data frame from pandas. You put your partitions, and then it would just be the same thing. You can just put this here. And this will work off the shelf. So I won't run this, but the point is that however size of data you have, next level scale is very seamless. You just have to change the data that passes in. And then with that, I will move on to the next section. So we got an intro to stats forecast, and then now we're actually going to we're going to apply it on some data set. So we're going to look at what that data looks like and process it in some way. And then we will do the hierarchical forecasting. So we're just looking at the data. And in time series forecasting, there's a famous data set, this M5 forecasting accuracy. So this is a Walmart data set. And it contains, so here, 3,000, let's say roughly 3,050 products spanning 3 categories, 7 departments, sold in 10 stores across 3 states. So it's a sample data set, but it's already quite a bit of data. And this is where we have that kind of hierarchical relationship that we want to preserve. We have 3,050 individual products, and then we have them at the category level. I think it's department level, category level, store level and state level, right? So we want to preserve all of that. So I already uploaded this in an S3 bucket. So if you just run this, it's public. You can just download it, no problem. There no authentication required. And then I already have the code to extract that file. It comes in as a zip file. I extract it, and then what you'll see is you have these data sets. These files. So you have the calendar, the sales train evaluation, and sell prices. So we're gonna just look at each of these, like the first couple rows for each of these. So for the training data, this is what it looks like. We have uh, this ID is like a unique identifier for the whole row. Like this, each row here, by the way, contains a time series. So we have a unique identifier. We have the item ID, department ID, category, state, store ID. So there's CA1, CA2, CA3, state ID. And then this over here, this D1 is literally the day one of our time series. So if we go all the way, we have 1,941 days. And each one of these is each one of this is a daily measurement. So this is our date. Each row is a unique time series. And the reason that it's actually, I mean, it's a weird format for working with in terms of like modeling. If you remember the format we had earlier, we had unique ID, DS, and Y. So we have to there was someone who asked earlier, I think it's Ahmed, where like, how do you start? So we need to figure out how to transform this data set into something that's compatible with stats forecast. The reason it's stored this way is because if you stored one day for each row, then you have 1,941 rows to represent the time series for each product. And then you multiply that by the 3,050, right? So you end up with a lot of rows, and this is one of the ways to compress it, right? Where you just this in terms of memory, this is a lot lower than if we had one row per day. Sell prices, this should be pretty straightforward. We have an store ID, item ID, though this is like the specific week of the year, and then the sell price. So the sell price changes per year. And then the last thing is the calendar. So you'll see the calendar has the week of the year. And then, so here, we're gonna see a full week, like this is 2011, 129 to February 2. And that's a week, and that's why they have the same value here. And then the rest here is just like month, year, day. These ones, like, I mean, we're not too concerned about accuracy today. It's mainly just like we're just concerned about the main workflow. But these events can be stuff like, oh, it was the Super Bowl or something, like Mother's Day or stuff like that. That's in the data as well. And then SNAP is like the federal assistance program. So some of the products I think are eligible for SNAP. Like I don't know what to call them, but you can use the federal assistance to purchase those products. So we're not going to really look into that today because we're not too concerned about performance, and it adds a lot of complexity. So we want to see what a time series looks like. We have just a snippet here. We have to. This is the important part. If you remember our data. Um, Gotcha. So Robert added more detail that Snap activation dates are important because it drives demand. Gotcha. So here we're gonna plot a time series, and what we're gonna do is we're gonna get that day one to day 1,000, like 941 or something, and we're gonna transpose it, and then you'll see what the data will look, and then we'll plot it. So the date this is what one time series looks like. This is the hobbies one, product 234. right? So this is what one time series looks like, and this is what another time series looks like. And you're gonna see, I think these are points where it was out of stock. And this is a third one. And you're gonna see that I just want to point out the y-axis. So this is 0 to 120. This higher one goes up to 700, 800, and this other one up to 250. So we have a bunch of products, and this is why in some cases you actually just train a model for each individual time series rather than training one, because then you're able to, I mean, there's debate for either way, but then you're able to capture the local like local time series context, and you can have a more accurate model sometimes for that. So next steps, we looked at the data a bit, and then we're actually gonna pre-process it. Um, I feel a lot of people get a bit lost in this section where we pre-process the data because there's a bunch of transformations. So I will actually just focus more on skimming the actual transformations and maybe just focus on what the output looks like. And then we can move on to the hierarchical forecasting section. So this is just here we're gonna use Fugue to pre-process the data. So if you remember what a row of this training data look like, we have our day 1 here all the way to day 1941. But if you remember the format Nixla expected, Nixla wants it to be vertical, right? So we have to transpose it in some way. And here we have this is just checking what the calendar has. Again, we're not going to use events or snap. We're not interested. I mean, we're not trying to improve accuracy. And then here we start our transformation. So this is a so I should preface this by saying that the library that I work on, Fugue, what it does is it lets you take Python or Pandas based functions and apply them like with multiprocessing or on top of distributed data frames like Spark, Dash, and Ray over a cluster, right? But the important part is that you can define, like if you look at this piece of code, it has nothing to do with Pandas. It's just looping over that data frame that we had. And this is just vanilla Python. So each row comes in as a list, right? And here we're looping through the columns. So if you look here, everything past column 6, so 6 meaning actual 7 in Python, right? I think. So 1, 2, 3, 4, 5, 6. Oh, sorry, 6 columns. Everything beyond this is the time series. So what we're doing in this function is we're looping through the every column past the 6th column, and then we are adding 0.01. So this is a common like numerical stability trick in time series modeling. A lot of times, if you have a lot of zeros, you can get division by 0 errors. Stuff doesn't converge. So a lot of times you'll see what people do is they just add a very, very small value to the forecast for numerical stability in the training process. And then we just return that row like a new row. So for each day, we're just returning one whole row with the elements before, and then we just add the elements after. So we will retain 1, 2, 3, 4, 5, 6. We will retain all these columns, and then we'll just create like a column called Y and have all of the vertical, make this data vertical. So I think you should have, so we have this function, and Fugue is that intermediate layer that takes this function and applies it to a pandas data frame for us. So here we apply it, and then this is what I'm saying. Don't be too worried about the transformation. The more important thing is the output. So this is the format that we want. If you remember, we had in our generated time series, we had unique ID, we have our date, and we have Y. So the important thing is we already have the 3 columns that we need in order to make a forecast. And then, so this is pretty much it. And then I think what we're gonna do, this is just distributed stuff. So this is uh, how so similar to Nixla, where the data, like if you run it on so smaller data, big data, the syntax doesn't change. This is just the same thing, where we are just using Dask instead and passing it as the engine. All of the other code is the same. The point is that we're just using Dask for parallel processing here. So not too important, but this is just to this actually took me like 5-6 minutes to run. So that's why I'm not really running stuff live. But the point here is that we just multi process, and then we can get this format faster because it's actually quite expensive to make this process. So remember the point one is just that numerical stability thing. And then something I didn't cover in the first section when we had the intro is what we call exogenous regressors. So if we do something like, if we use a model like AutoArima, what it does is it just uh so like, let's say for those who are not familiar with AutoArima, there's three components to it, right? The AR, the I, and the MA, and that's why it's called that's why it's called ARIMA. So the AR is the auto-regressive. So like how correlated is a time series with like the previous value, with two values before, with three values before. The I don't think is as important. The I mean, it is important, but not necessarily in this context. And then the MA is the moving average. So if we get the moving average for the last like 7 days, how does it affect the next value in the forecast, right? And all of these things that we're using, the autoregressive component and the moving average component, are inherent to the time series itself. So what happens if you want to add events, the snap, the sell prices? Then we need what we call exogenous regressors. So exogenous meaning it's not part of the time series. So here we have the sell price. And the important part is that we just do some joins. And basically, in the output data, remember we had this already. We just joined these two. So now we have the sell price uh, for each week. I mean, for each day now. And this is important because it could affect purchases also, right? So once we have that, we can run our stats forecast again. So we have our combined data frame over here. It's going to look like this. And then we just keep the unique ID, DSY, and the sell price. So you're going to see some filtering around here, I think. Oh, so I just do it for one here, just to demo what it will look like. And um, okay, so I sampled it. I literally just got one unique ID. And then I got the dates for that period, and I got the sell price. And then what you can wait, sorry, I'm not sure this is right because I seem to be using no, sorry. Let me repeat that. So I have this combined here. I filter for these four columns: unique ID, DS, Y, and sales price. So this is the most important line here. I just have these four columns. And I pass that to the stats forecast object. And this is same as we've seen before. We just run AutoArima on this. This is nothing new. But the important thing is that if you're using sell price as a predictor in your model, then you need to know the sell price also when you make the forecast, right? So if I use an exogenous regressor and it's actually influencing my time series forecast, I also need to know what the value of that exogenous regressor will be in the future so that I can make the forecast with that information. So if you're using an exogenous regressor, you need the data out. You need the data related to your forecast period. So over here, I'm making a data frame where I am just making a new sell price and I'm just filling in the next 7 values. That's why it's 3.97 times 7. So I have a list of, like I have 7 rows. And then now I'm forecasting with this, right? So, and then you can get the forecast. So I will in the next section we're going to explore hierarchical forecasting. And this would be a good time to ask questions. So Ahmed is asking, how do you get Fugue set up in my environment? Should I use Jupyter Notebook? No. So this repo, I have over here a clone repo. I mean, sorry, I have a repo that you can clone, right? And I'll put it again. And the important piece here is that you can clone this uh, over here. And the important part is this Python requirements.txt file. So if you wanted to replicate it, there's two things you need to do. So here you would pip install. I mean, you create a virtual environment or something, and then you pip install the requirements.txt. So this is one thing. And notice my environment is the PyData environment. So if I actually wanted to run it, I have to make sure that my notebook is also selecting the PyData environment, because that's where I installed everything. And then, but I would say Fugue is something more potentially intermediate, and it may be a bit tricky to understand what Fugue is doing in this notebook. So I think for you, maybe the best thing to do is to just see what the output format looks like and then figure out how using pandas. I don't know, Fugue might be easier. For me, it is. I'm not sure if it will be if that will be true for everyone. So maybe just worry about, like, if you want to replicate this, okay, how do I get that row and pump it out into this format right over here that we saw. Oops, I'll bring this down. This format. The important part is you want a format like this. Something that you'll also see in this notebook is that we save things into Parquet file as opposed to CSV. So if you're new to data, you'll more commonly see CSVs, especially because there's a lot of utility with CSV. Like if I have a coworker who doesn't know Python, I could give them a CSV. They can open it in Excel and they can edit a value, right? And then we could, like, work on the same thing. But I think for data at scale, you want to use Parquet files instead. And this is just the same thing. Like if you're using Pandas, Pandas has this syntax, right, where they say to CSV, and then you provide your file name over here. And then you say index equals false. There's also an equivalent to Parquet. I think it's like this. And the reason you want to use Parquet is because this data can be a bit big. So number one, Parquet has, in terms of this space, it's uh, around 1/5 or 1/4 the size of CSV. So for the same file, there's a lot of compression, and the compression will help you both writing and reading. So CSVs can be notoriously slow to read. The second thing why you want to use Parquet is because it preserves data types, right? So a lot of times when you use CSV, you load the CSV in, Pandas will infer the schema, and then they'll infer it wrong. So maybe they see a timestamp, they think it's a string, you have to convert it to a timestamp again. Parquet, on the other hand, holds that information. So it's more consistent when you save and load. There's no schema inference anymore because it's attached to that file. So Parquet is heavily preferred. Unless, again, you work in an organization where, like, I need to give a non-technical person a file and they need to be able to edit it. That's the use case for CSVs. But like in a lot of projects, I would just download the CSV, convert to Parquet first, and that tremendously speeds up the iteration process also, because it's a lot faster to read in, right? Compared to if you have to read in the CSV multiple times and it takes forever. So we have our data format. The most important piece is we have our data format over here. And then we're going to see in the next part how we perform this hierarchical forecasting. And yeah, a good time to ask questions. Otherwise, I will just move on. Um, I'll give it. I'll give it 30 seconds. I mean, I can talk forever, but I'd like to give other people a chance to talk also. Okay, then. So if there's no further questions, um, literally any question is fine. We can also go back to first notebook if you want. It doesn't even have to be on topic. Also, I'm happy to chat about anything. So I'll wrap up this hierarchical forecasting notebook, and then
Let's keep things on topic, at least for now, for the recording. Afterward, we'll chat about everything.
okay,
Okay.
okay. I'll finish hierarchical forecasting, and then I'll briefly touch about how to scale it out, but then I won't go so deep into that. So with hierarchical forecasting, I've mentioned this a couple of times. What you want is like, for example, your store level, or there's a better one here. You want um, your region. If you add it up, you have forecast at the state level, and if you add this up, you have forecast at the country level. And the thing is, you want all of these to be equal to each other when you do the forecast. And this is I see this most often in companies that do stuff like logistics, supply chain, retail, stuff like that. And the important concept with hierarchical forecasting, the term here is coherent. So coherent is that term where if you add everything bottom up, it sums up to the top. That's what we call coherent. So how do we produce coherent forecasts? So there's two steps here. Number one, we create a base forecast. And then number two, we will we will reconcile what we call reconcile those base forecasts in order to create the coherent forecast. So the hierarchical forecast is the library that we can use to make the for step two, that coherent part. And we have a couple of algorithms we can choose from. um, I honestly can't tell you like if one is better than the other or not. I think it's kind of similar to machine learning, where like you try multiple things and see what works best. So let's work on our previous data set, and I am going to get, so instead of auto ARIMA, auto ETS, I'm getting these models instead, just primarily because like the auto ARIMA fits a lot and can take a while to train. So these ones are more defined. Um, and then these are our hierarchical reconciliation methods. So we're getting this reconciliation, and we need to provide a method. So bottom up, meaning you sum everything from the bottom to the top, and then there's also top down. There's also middle outward, and then min trace I'm less familiar with. Um, and so here we have our previous data set. And what we want to do is we want to forecast for each unique ID. And again, because we know how to do it in stats forecast, sorry, so there's a couple things we do before that. We're just exploring the hierarchy in this, and we're exploring the hierarchy first here. So so in this tutorial, we focus on a single item, and we want to create the coherent forecast. So here we just get, this is pandas code. We loaded in our data. We have a hierarchical data frame over here. It looks like this. And we would just want to get the unique ID to focus on for hierarchical forecast. So we have an item ID, and we're going to query by that item ID, group by, and then sum. And we're just going to see how many unique time series we're working with. So that once we queried by this, we are now we're operating across 3 states, 10 stores, and then this is the date time. So that's the number of days in our data set. So but the important thing is we have 10 stores here that we want to roll up, right? So we have 30 individual time series, but then we want it to be equal at the sorry. We want the store forecast to equal the state level forecast. So here we create a top level because when you do the hierarchical forecasting, you need a root node also. So our root node is the US level. So we're inserting this US into our data frame over here. So this is the total. So it allows us to group by sum on this column so we can get the USA level forecast. Now, after that, there's this aggregate function is something from the hierarchical forecast package. I am trying to just scroll up so you can see it imported. I'm not seeing. Oh man. Anyway, just this aggregate function is imported from hierarchical forecast, and what it does is it returns three things from us. So we pass it in our data frame, and along with the hierarchies over here. So total is the USA level, and then total and state ID, right? And then up to the store ID. So we have these, and then what it does is it returns us three objects, right? So number one is it returns to us all of the data frames summed for each level of hierarchy. So here, if I look at the hierarchical here, you're gonna see that we have a USA level, and then for each state, you're gonna have a time series also. And then the S is the summing matrix. So the summing matrix is like what individual time series add up to this other one. So if I look for the USA tag, I mean the USA part of the summing matrix, you're gonna find that the USA is composed of these 10 time series. And then the tags is also just a matter of which time series are tied to what. And when you do, so what happens is that so the tags is just a dictionary for each level, which are the associated time series. So S is a matrix, tags is a dictionary. And what you're gonna see is that these two, after we perform this aggregate, we just have to pass them into this hierarchical. So this is just for plotting, but we're also gonna pass them on for the modeling portion. And now we have this utility function. So we can say plot this tag, and then you get a time series like this. I mean, a plot like this. So we have the data at the USA level, and then we have the Wisconsin level, and then we have the Wisconsin store number 3 level. And it just lets you visually, so you can see on the y-axis, this rolls from the bottom to the top. So the middle one, Wisconsin, has 3 stores, and then the USA level has 10 stores. So here our axis is from 0 to 200. Our axis goes from 0 to 600. Here it goes from 0 to 2000. And now here's what I was talking about. I will not use Hugh here. Here we said we needed the base forecast. So now this is the same thing as you saw before. The only difference is the models here. I'm using different models, but it will be the same if I use AutoArima or AutoETS. I just chose models specifically that are faster to train in order to speed things up. And you don't really need, this backend is old, so you don't need this anymore. And then now you can just use this forecast SF dot. You don't need to worry about this part right now. This forecast is the same thing as before. The reason we call dot compute is because a while ago here in my code, I actually converted to a Dask data frame. Or sorry, I'm using a Dask engine to parallelize it. And so the compute is like converting a Dask data frame to pandas. But if you were pandas all the way, you don't need to worry about this. And then after that, we check for the sum for each hierarchy. And we can see that if we look at this forecast over here, we have a total forecast, and then we have this is the total if we add each state, and then this is the total if we add each store. And this is what we're talking about. So we just did stats forecast, base models, and then we added them up. And what you're gonna find is that most often they're not coherent, right? So these don't equal each other. This even has a difference of 500, right? From total here to over here. And so like if you're doing something like logistics, it's hard to figure out which prediction to use because they're not coherent, right? And that's the value of coherency here. And no, so none of these models generated any coherent forecast. Ahmed has a question where to find the recording. Jacob, I guess we'll mention later where to find the recording. And then here, once we have our base forecast, so I said there's 2 steps. Number 1 is you do your base forecast. Number 2, you do your hierarchical reconciliation. So here I have a list of reconcilers, and it's the same thing. I just have to pass them to this hierarchical reconciliation object, and then from there I just call dot reconcile, and I just pass in. Remember, I have the summing matrix S, the tags, which is the dictionary, and the forecast that contains all of the levels of for like a USA forecast, store level forecast, and even in individual store level forecast. And that's it. Now you come up with the reconciled forecast, and what you're gonna see here is that so this is a this is the base forecast, and then this one over here so IMAPA, MFTL, ETS are our models. IMAPA bottom up, MSTL bottom up, ETS bottom up. They are the base model plus the reconciliation. And then that's why the value could be a bit different, right? For some, you should see them being a bit different. And then the other one is the min trace. So this is just another reconciliation. So we have IMAPA min trace, MSTL min trace, etc. I guess we're not really seeing differences here, but maybe it's just for this particular unique ID, but for other ones you should see differences. And then now we can calculate the sum per hierarchy. So we tried 3 models, if you remember, and then we have our bottom up and we have the min trace. Bottom up meaning just you add from bottom up and you just reconcile them. Min trace, I think this is the most expensive. There's an actual regression that happens here. And what you're gonna see is that now if you look at the first 3 rows, they should not be equal because there was no reconciliation, right? So this is the clearest row. You're gonna see there's a lot of fluctuation in the value. But then with these reconciliation methods, it's now consistent across a row. So here, this is consistent, this is consistent, this is consistent, right? And then you can also plot the link series, and this is the linked forecast, right? So you can see there's some seasonality going on with this time series, and it's captured in all 3 levels. There is a next section here that talks about cross-validation in time series. I think I will not cover this today because it can be a lot. And then the last thing
We can talk about for the recording. You're good. Go on.
Okay, and then the last thing is running on a cluster. I will just say that actually, so here I do my pre-processing on a cluster. So there's 2 steps, right? One is the base forecast, and number 2 is the reconciliation. And the base forecast is easily parallelizable, right? I have 100,000 time series. I just do 100,000 time series. I forecast each one. It's not a problem. But the problem is the reconciliation part. So you can do the base forecast on a cluster, parallelize, no problem. The tricky part is the hierarchical part because there's a covariance matrix that is calculated, and the covariance matrix, I mean, the size actually goes up by so each you get the covariance of each time series with all of the others, right? So you can think about it. If the time series is, if you have 1,000 time series, your covariance matrix can have 1,000,000 elements, like 1,000 by 1,000, right? N squared. If you have a million time series, it also goes up, and you have to store that in memory. So because of that, the hierarchical part is not distributed, like parallelizable right now. That's not to say it is not parallelizable in theory. It just has a higher degree of complexity, and we haven't gotten to implementing it yet on the Nixla side. It's one of the things assigned to me technically, but we'll see. But hierarchical forecasting, you so if you what I've seen people do is they just forecast on a cluster, and then they get the for that step where they want to reconcile a lot of things, they just load it in a bigger machine, execute it, and then spin down the bigger machine. And I think that's a good place to end. Yeah, notebooks are available, and I'll stop sharing there. I've been talking enough.
So first of all, let's thank you before more questions. So make some noise.
Thank you.
I think you can unmute yourself, make some noise. We're making some noise for Kevin. So if anyone has any
Thank you.
Yeah, anyone has any questions? Come on.
Yeah. Question here, and apologies if this was covered and I missed it or something like that. Is there a way to sort of summarize about how the hierarchical models sort of do that consolidation that they do? Is it like, how do they choose, like, you know, they're trying to get, you know, like a group of models to fit, you know, into this one, you know, it's got to be, you know, it's limited to sort of like, I don't know, say 100 values at one time period or something like that. How do they choose which model, you know, grows and which one shrinks or something like that? Is there some understanding of what's going on under the hood there?
Yeah. You're not reconciling the models per se. You're reconciling the forecast values, right? So it's just a matter of which you prioritize. Do you forecast? Do you prioritize it at the store level and then roll it up, or do you prioritize the top forecast as your ground truth and then bring it down? You can think of it like that. And that's how the bottom up method and top down works at the gist. I'm not I'm not technical enough on those to provide more implementation details. Um, and then the I would say the min trace is where it gets to be like more of a regression type thing.
Oh, okay. Yeah, that makes sense. That it's sort of like each model's output is sort of like a variable into almost like a regression type calculation.
Yeah, and then just a matter what you define as like the ground truth. And then it will just like meet in the middle, so to speak.
Cool. Thank you. Ed, great talk. Thank you.
Thank you.
More questions? Come on. You didn't understand everything. I didn't understand everything.
I have a question.
Go ahead.
How long in your experiencing learning programming do you feel like you were able to figure out how to put together these sorts of notebooks and these forecasts?
Sorry, what was the last few words? You said these notebooks and these what?
Forecasts. Yeah, because I'm at the point when, yeah.
Yeah, sorry, go on. You're at the point where?
Well, I'm at the point of like I'm still in the beginner's point in Python. Like I've made let's see, a rock paper scissors thing. I'm trying to get into GeoPandas. I made some sort of system thing that's supposed to like just create the directory to the desktop type thing. And I'm just like not exactly like from where you were back during, I guess, school to where you are now. How much do you feel like it took for you to figure out how to do all of this?
Yeah. So So when I graduated my master's in 2016, and I became a data scientist in the start of 2017. Between 2016 and 2017, I self-studied Python for 6 months. I would say that it's just like, whatever I tell you about my experience may not necessarily be the bar. I mean, okay. Oh, sorry. I was jumping the gun. If this is in the context of like, um, what skills do I need to be competitive to get a job, then it's like a broader discussion, because like when I graduated in 2016, and the market was like, hey, you're a engineering masters that can code and maybe one course, like that's good enough, right? So it's always like the ability to get a job is always relative to what people are doing at the time. And it just so happens right now we have so many courses and boot camps and stuff. So the bar to get a job just becomes higher, because ultimately you're competing against who's in the same job market as you. Um, but if you're talking about from a confidence standpoint, like where I feel like, when did I feel that I was like comfortable coding and stuff like that? Mm, I mean, I don't mean to scare anyone here, but like, I mean, it's been 7 years, but I still feel like I'm learning a lot. There's just so much to do, and and I don't mean that in a bad way, right? It's just like there is really that much, right? Like in terms of what I presented today, I specialize more in the distributed computing side and the large scale side, and I'm less of a time series person myself. I just help these guys are just friends, and I help them scale out their libraries to run on clusters. That's my main role, but I won't be able to provide as much information on the actual time series algorithms. So it's just a matter of like, I feel like there's just a point where you just start to specialize, but you never stop learning, is what I'd say. And I invite anyone else who is more experienced as well to chime in to answer this question. And then the next thing I'll say is that, but in order to make like a notebook that, like, hey, this is a notebook end to end, maybe training a machine learning model, and getting it, I mean, like maybe plotting some stuff and exploring data, maybe 6 months to a year to get like those initial notebooks. But that's still very far removed from putting things into production, so to speak.
That's true. Yeah, let's see how I say this. And is this you say this while you're working full time, or is this sort of I'm or is this sort of a like spending every hour of the day sort of working on it type of um time
Hmm.
thing?
Do you mean when I was job searching, or do you mean what I'm presenting now?
In terms of like you say, like people say, like I learned all this self-learning
Mm.
programming in 6 months or so. It's like, okay, are they working a full-time job? Or are they a student? Are they like between jobs when they're doing this?
So I've like some people message me for career advice, and I help them like get their, like, just like get their foot in the door, so to speak. And you're welcome to message me as well after this. But I'll say I feel like if I give a benchmark like that, I think it just varies too much between person to person. And what I find is
Mm-hmm.
just that ultimately, like, for example, if I told you that it was 6 months for me and you end up spending more than 6 months, I feel like people end up getting depressed. And I don't think it's reason to be depressed, because like we just all have our own rate of learning. And there are even people that when I look at them, it's like, wow, how will I ever compete with them? Like, but then like I feel like you shouldn't necessarily compare, right? Because that just leads to more frustration. And I think it's just a matter of just being more focused on whatever you have going on and doing things at your own pace.
Um, let's focus questions. We'll have more time after the recording ends to add more questions on whatever topics. But let's take. Does anyone any questions for what Kevin presented, the time series stuff. Well,
You
any
guys,
questions in that direction?
Can you hear me?
yeah, I hear
Tyler.
you.
Yeah, I have a question. So when you kind of approached this Jupyter notebook and you started to do some of the data pre-processing and then doing some of the time series graphing, what was your first approach? Like, how did you come to like getting the requirements to know what to code? Like, so do you start with kind of understanding the different statistics and then you go and then you find the libraries to kind of fit that, and then from there that's kind of how you start your to get to the point of coding in the graphs? I guess I'm just wondering, like when I'm looking at it, because I don't come from a big data science background, I come from mostly data engineering. My perspective would be like I would have to like really dig deep and learn some of the statistical side of things. But then when you get to the implementation side, there's a lot of different things that Python offers or some of the different libraries. So I don't know if you could speak about like what level of statistical knowledge should you bring to the table before you start to try to do some of these things, because it seems like there could be a lot of different libraries out there and there could be some trade-offs and you may not understand the level of accuracy of some of the different libraries that you're using and presenting, or some of the different inherent biases associated with them.
Yeah, I'll answer Tyler and then I'll get to you, Anupam. With Tyler, I think um, I guess the question is what your end goal is, right? Because I think there are a lot of, like you said, you're a data engineer, right? And I think I can think of, like, for example, there's full stack front end engineers and they want to incorporate machine learning in their app too. Like, for example, they have time series in their app and they just want to get a forecast up there. They don't necessarily need to know the internals of time series forecasting. All they need to find is a service where they can throw their time series and then get a forecast, right? So I'll say that the level of which you feel like you need to understand things is very dependent on um like what is, because it's all a means to an end, right? So it's all about like can getting to the end, right? um and whatever way has least amount of friction for you, right? So if you're evaluating multiple time series libraries and you find that one you can implement in 5 lines of code and the other could take 50, maybe you try the one with 5 first, right? And you see that it's helpful. Um, and if it's not satisfactory, then you move to the 50, right? So it's ultimately dependent on your end goal. But number two, um, your question is like, how much statistics do I need to know? And I'll say that, I mean, yeah, yes, statistics is important, yes, but like if the goal is to get a job, okay, you might need a bit more to be a professional. If you just want to try your own thing, by all means, like you're always welcome to, right? Like we can all be, we can, there's nothing stopping us from trying, right? Because like there's just so much material out there available. But if you're thinking in the context of like a career transition, um I will say if you're already a data engineer, it's like maybe you just want to. Number one, I think I prefer data engineering. I was a data scientist. I think I prefer data engineering because my milestones are more concrete. But number two, you probably already have access to data. I hope, maybe. Just try tinkering with that and seeing what you can come up with from the machine learning side. Focus on getting an outcome, not necessarily on accuracy or rigor, because there's value in both, right? And these days, I find myself more specifically as a machine learning engineer, where I put data science work into production, but I do much less data science these days.
Okay.
Uh,
Yeah. Thanks. Thanks. That helps somewhat.
okay.
Thank you.
Anupam?
Yeah, hi. Thanks for the excellent overview of what you're doing. And, you know, time series is complicated and fascinating at the same time. So I have some, you know, maybe broader questions about time series. So the way I understand it is that there are maybe two approaches. One is that you keep looking at small changes happening in the data to trace the path into the future. And the second is you actually look for patterns and then try and find out what's happening. So what if the structure of the system, which is from where the variable comes, itself it has changed? So for instance, what would happen if you were to look at pre-pandemic and pandemic data? Would this forecasting work as well? Or would it completely throw us off what to expect?
Are you a machine learning practitioner?
No, not really.
Oh, okay. So in machine learning, like this pre-pandemic, post-pandemic thing is a good example, right? And in general, so I have two answers to your question. The first one is that in general, this thing is called model drift, right? Where it's like maybe this model was trained in like 1 year ago and it's not applicable in the real world anymore, right? So when it comes to model drift, I did a project during COVID for the government with regards to social care, and I'm like very concerned also about the model that I made, if it's making right predictions, and we hope to continue that work, but they don't have budget for us to continue, and we're kind of worried about that. So but in practice, you refresh the model by training consistently, right? And that's how you overcome model drift. So if you're training your model and you're deploying a new model every 3 months, for example, it can, I mean, aside from that abrupt shift in COVID, like in general, you're not always too far off from the real world. So, and then in the time series forecasting, we kind of make forecasts every week, so to speak. So it's kind of, you're never really going to be too far off as long as you increase the frequency of your predictions. So that's number one with model drift. Number two, the way you phrased your question at the start is like, can time series be used for anomaly detection, right? And the answer is yes, it can. So what you do is you just plot the 95% confidence interval around your prediction, and then if you, or 99%, and if the actual value that happens is outside your 99% prediction interval, then you can flag it as an anomaly and raise an alert. So you can also use the same type of time series models for such a case.
Thanks, that helps. Just a follow-up to that. So you think that black swan events can actually be caught in this?
Yeah, I understand. I think there can be an alert of it, but you won't necessarily be able to make sense. And for everyone, I guess, and correct me if I'm wrong, but the definition of a black swan event is like, you know, an anomaly where something happened and there was some fundamental shift and you want to capture it. And you know, I have a friend who was very interested in this because he was actually trading cryptocurrency, and the exchange, he caught a time when there was a lag in the exchange rate and between the US exchanges and the Philippine exchanges. So he was able to, you know, get arbitrage, so to speak. And he was trying to detect for these events. But, you know, like, I feel like it's easier said than done to detect black swan events, because realistically, if you try to make such a solution, number one, you have to know what to look for. And by definition, with black swan, you don't really know what you need to keep an eye out for. And then number two, with any type of system that raises an alert, a big concern is false positives. Because if your system raises 10 alerts and 9 are false positives and 1 is real, it's arguable that you'll be able to act on the real one, right? And I think with black swan events, it can be tricky because you're going to have a lot of false positives and making the system not so effective, you know?
Okay, thanks.
So, Kevin, I suggest, unless someone has a pressing question they want to ask about what you've shown, maybe we'll stop the recording. Is it okay with you?
Yeah. Anything's fine. Yeah.
Okay. Anyone has anything pressing? Questions going once? Questions going twice? Don't go away. We're staying here. We're just stopping the recording. Questions going the third time? Okay. No more questions.
I'll ask. I got one question.
Go ahead.
This is Jeremy. So I contract with a company that does background checks for companies, their clients, and they wanted to do forecasting in the past, and I've helped. It's been very simplistic, but how many like variables can I start to pull into these methods? For instance, so if there's a client that wants to do a background check on an employee, they order a background check, and part of that, you have to check that person's criminal history, check their employment, check there's education. So there's all these different types of searches, like in what you were showing, different types of products. And going down to the granularity, I create a forecast on the volume of searches, over the span of time, based off of the prior year on the amount of searches that are coming in for employment checks, education checks. But then on top of that, if we want to forecast like workload for employees, different types of searches have different types of like turnaround time. So if you need to work on something on a daily basis, one search like verifying education, you may have to work on it for like a span of 10 days before it closes out. So it requires like 10, to work on it daily for 10 days. Where another type of work might only require, it's a one and done situation. So trying to forecast the amount of workload per day, like assigned to various departments, as well as like factoring in staffing and people's vacation and how that impacts it. So if you want to just do a simple thing where it's like, all right, I want to forecast workload for a time series, but I also have like 5 to 10 different variables that can really alter how that forecast works. Can you just, that can maybe get complex and more than I'm, in my first run of things to be able to do. But is that something that like with the libraries that you've shown that is obtainable?
Yeah, so I have two answers for you. Number one is that if you want, what I showed is a very statistical and econometric based approach. But if you want to do time series forecasting with features, Nixla also has a library called ML Forecast. And the way it works is like the forecast is like you add your features, and it's like an XGBoost model or scikit-learn model that you use as your model to perform the forecasting. So it's called ML Forecast. So if you want to go that route, there is that. But number two, I am actually skeptical that your problem should be framed as a time series problem. And the reason for that is because I had a similar project, and I'll just explain what my project was. And we can talk about it like significantly more, how we approached it offline. But my project was and I mentioned I did something for the government during COVID. What I worked on was a social care. It was on the social care system. So basically, caseworker A maybe has 10 kids, and caseworker B has 9 kids that they have to take care of. They're social workers, right? And working on the foster care system. And a new kid comes in, and the manager would just say, oh, caseworker A has 10 and caseworker B has 9, so I'm going to put that kid in caseworker B's hands, right? And what we were working on was, okay, how do we actually identify the complexity and the workload attached to each individual case when it comes on that screen? So if we can make like a point system of estimated workload, like caseworker A has 10 kids, but if we can estimate that currently today or for the next week, he has 30 points of workload, and caseworker B has actually 40 with his 9 kids. If we can run the prediction on the kid basis and the workload per kid, then we assign that kid to caseworker A right now, right? As opposed to caseworker B. There are some scenarios that have very high complexity. Number one is if you have siblings, for example, that are split up in the foster care system. Number two, for example, is like trauma, abuse, that kind of thing. Compared, like that can be have additional resources. And then older kids can also be complicated. So we actually predicted it on the workload level of each kid. And then that the workflow that you described, where you have to forecast the workload, that just becomes a management decision that's done on a day-to-day basis, right? So today the manager opens their screen. These are the workloads. This is how we distribute the new cases. So you don't necessarily have to forecast the workload of over time. It's just like you approach it week by week and you treat it like as a point system, if that makes sense. So that's another way to frame it. That's not necessarily time series, if you will. And we can chat about the specifics more also.
Yeah, no, that makes a lot of sense. I appreciate the insight.
Yes, Anupam?
I thought, this was interesting, the question that Jeremy just raised and your response to it. I was reminded of what Cesar Marchetti from the International Institute for Applied Systems Analysis had been doing for almost maybe 50 years of his life. He was using simple Lotka-Volterra curves in order to come up with forecasts for technology, for even things like productivity of people, particularly artists and musicians. And I just shared in the chat a link to his approach, and where he actually talked about how Mozart and Bach and Beethoven started, how they performed during their age. So some very remarkable work in terms of forecasting things which we feel are very difficult to forecast by using simple Lotka-Volterra curves. You might find it interesting.
Mm.
Thank you for the share.
Yeah, for us, it wasn't an estimation thing. It was, we knew, or I mean, it kind of was, but for every caseworker kid relationship, we had a log of their activity, and we just assigned like 30 minutes, 1 hour, 2 hours, and then we could just roll it up, like what the hour count per kid is. And then the predictive part is saying, okay, how many hours in the next month is this kid gonna take? So there is some machine learning and there is some predictive, but you're estimating a point in time workload, not like a forecast workload.
Okay, so unless there are really questions about the time series or the hierarchical ones, then we can continue the discussion afterwards. I just want to close the recording if it's okay with you guys. So anyone wants to go on record with any more questions, or can I stop? Okay, so we're going to stop the recording, but before that, let's thank Kevin again. Make some noise.
Yeah, thank you for
Thank
having
you,
me.
Kevin.
Yeah, well, don't go away. We're not leaving. We're continuing this.
No,
Thank
I'll be
you.
here. I'll be here.
Thank you all. I'm gonna stop the recording. Here we go.